This demo shows the pilot scenario 2.1, which focuses on demonstrating how the ELECTRON platform blocks vulnerable assets from accessing the OT network. Within the electric vehicle charging infrastructure, supervisory control and data acquisition systems, or SCADA, usually operate and provide auxiliary services, including collection of operational data from the embedded energy meters of the EV charging stations, as well as overall status monitoring of the EV charging and electricity infrastructure. However, SCADA operation is based on legacy and vulnerable communication protocols, like Modbus TCP. Moreover, legacy host systems may be used for hosting dedicated SCADA software, for example deprecated Windows operating systems. All these systems introduce vulnerabilities that could threaten the integrity of the EV charging data, or be exploited for gaining internal access or performing lateral movements in the OT network. Before starting the demonstration, this is a summary of the steps that will be followed by the ELECTRON components in this scenario. First, the ELECTRON SDN controller and dashboard discovers the network topology, initializes the SDN switches, and scans the assets for vulnerabilities. Next, the ELECTRON Army component retrieves the topology discovered by the SDN controller, and performs risk assessment based on the identified vulnerabilities. Next, the ELECTRON DASI component suggests mitigation actions for assets and vulnerabilities, by using manufacturer usage description files. Mitigation actions may refer to the correct configuration of an asset, and/or remediation for a vulnerability. With the mitigation actions, the ELECTRON Army component generates complete risk assessment reports. Finally, the ELECTRON NERO component receives the risk assessment reports, and decides on the best course of action. Depending on the decisions, NERO interacts with the SDN controller and programs the network switches accordingly. Starting now with the demonstration, this is one of the vulnerable assets of the OT infrastructure. It is a legacy Windows 7 workstation that is used by the charge point operator to access the HTTP-based web management platform for administering the EV charging stations. This asset carries vulnerabilities that must be mitigated, such as the CVE 2009-2512 vulnerability, which allows attackers to properly craft headers of WSD messages, in order to remotely execute arbitrary code. So, at the end of this demonstration, it is expected that ELECTRON will generate and enforce the appropriate security policies, in order to mitigate the CVE 2009-2512 vulnerability. Here we can see the ELECTRON SDN controller and dashboard component. In the home page, we see that there are 3 SDN switches currently connected to the infrastructure. Next, in the flows page, we can inspect the flows installed on each SDN switch. Table 0 is the entry point for all packets, while Table 100 contains the flows that permit normal communication between network hosts. Those flows have the lowest priority, since they need to be overridden by the ELECTRON security policies, which will be expressed as flows with greater priority. Next, we see a visualization of the network topology, depicting all the network hosts that have been discovered until now. More details about the assets can be retrieved through the asset inventory. The asset inventory agent has already populated the inventory with more information per asset. For the Windows 7 host, we see some basic information like the operating system and the URL of the MUD file corresponding to the asset. Some network information is also present, including the IP and MAC addresses. On the right side, we see the network services discovered by the asset inventory agent. The agent has discovered the WSD service, which carries the CVE 2009-2512 vulnerability that needs to be mitigated. Now we see the contents of the MUD file corresponding to the Windows 7 host. This MUD file consists of 2 root objects. The first one, which is the MUD container, provides some essential information according to RFC 8520, including manufacturer name, system description and external URL pointing to documentation. The second container uses the Medium-Level Security Policy Language, or MSPL, to describe software configuration policies. The MSPL policy informs us that the asset has reached its end of life, and recommends to upgrade to at least Windows 10. A relevant reference URL is also provided in the policy. This is the MUD file corresponding to the CVE 2009-2512 vulnerability. The MUD container includes information about the affected products, as well as a more detailed description of the vulnerability. In the MSPL policies container, there are mitigation policies, which suggest to block specific TCP and UDP ports, aiming to prevent the exploitation or further propagation of the threat. Now we are looking at the Army graphical user interface. We can see that initially we have not received yet the network topology and the assets. Moreover, we have not received yet any controls from the DASI component. Before initiating the synchronization of Army with the SDN controller, we should mention that it is important for Army to maintain an up-to-date knowledge base about vulnerabilities and threats. To that extent, concerning vulnerabilities, we can see that the current knowledge base includes vulnerabilities retrieved from public sources, as well as from the ELECTRON SharePoint, and from previous synchronizations with the SDN controller. With that in mind, we can proceed with the synchronization process. We have already created a new asset topology that is currently empty, and we can populate it by clicking on the Auto Generate button. The synchronization process has now started. By opening again the asset topology, we have received the topology, consisting of 3 clusters of hosts that correspond to the 3 SDN switches of the topology. Several hosts are attached onto each SDN switch. By going to the Risk Assessments page, we can see that a risk assessment process has been initiated automatically. In this risk assessment task, the vulnerabilities for each asset will also be considered, in order to calculate the overall risk for each asset. By looking at the summary of these results, there are 8 assets with very high risk level. Looking also on the heat map that depicts threat probability with respect to the vulnerability impact, there is one vulnerability with medium probability and very high impact, resulting to a high risk. By clicking on the asset for more details, indeed the asset refers to the Windows 7 host, and the high risk is caused by the CVE 2009-2512 vulnerability of this scenario. By looking at the notifications of the Army dashboard, we see that we have already received some mitigation controls from DASI. This means that, while we were inspecting the risk assessment results, DASI received the risk assessment report from Army, and returned back relevant mitigation controls. Now, we will see how DASI received and processed the risk assessment from Army. In this screen we see the main subcomponents, namely, the MUD manager on the top left, the threat MUD manager on the top right, the file MUD server on the bottom left, and the policy translator on the bottom right, which takes the MUD files and threat MUD files and translates them to the MSPL format. Going to the MUD manager, we see the risk assessment report received from Army. We also see the MUD URLs assigned to some of the assets. By using these URLs, the MUD manager receives the respective device MUD files from the MUD file server. Then, the MUD manager gives the MUD files to the policy translator in order to generate the MSPL files. Going to the threat MUD manager, it follows the same procedure with the MUD manager, but with the vulnerabilities instead. For each vulnerability, including also the CVE 2009-2512 vulnerability, it retrieves the MUD files from the MUD file server, and sends them to the policy translator to generate the MSPL information. Finally, DASI sends the MSPL information back to Army. Going back to Army, as we mentioned previously, we received notifications concerning new mitigation controls. Indeed, by going to the controls page, we can inspect the new mitigation policies. Some of them are related to threats, while some others to specific assets. For each control, we see the corresponding policies in the MSPL format. Having both the risk assessment results and mitigation policies, NERO will proceed on deciding about the best course of actions in order to mitigate the threats. Moving on to the NERO component, we see that NERO has received the risk assessment report with the Idaho 416. In this report, there are multiple threats with various risk levels. Depending on the risk severity, NERO will either apply the corresponding MSPL security policies or will ignore them. For the threats having very high risk, NERO will generate the corresponding mitigation actions, and will communicate with the SDN controller, in order to apply them automatically on the network. For example, we can see in the logs of NERO, that NERO has generated some SDN flow rules, which block network packets destined to the IP address of the asset and the TCP port relevant to the vulnerability. We also see the mitigation action applied by NERO for the CVE 2009-2512 vulnerability. The MSPL policy was converted to an SDN flow rule, which drops packets destined to the IP address of the Windows 7 host and the TCP port of the WSD service. Finally, in the SDN dashboard, we can inspect the flows that have been installed by NERO on the SDN switch. The flow rules generated by NERO have been inserted with a high priority of 30,000, thus overriding the flows permitting normal communication between hosts. 5 new rules have been installed, corresponding to the high risks identified in the risk assessment report. One of those is the flow corresponding to the Windows 7 host, blocking the 5357 TCP port. In this way, ELECTRON successfully prevented the potential exploitation of a vulnerability that carries a very high cybersecurity risk.